what's interesting is that if you look at, two things I want to say. Earlier, so this comes from the discussions in the break. So if you have questions, feel free to come in the break. I mean, you can also ask in between in the lecture, but you can also come in the breaks. I'm always happy to try to answer questions. So two things that came up. I showed you earlier how much air you need to burn 1 kilogram of hydrogen. And turns out there was a little mistake. That was actually only the nitrogen. You have to add the oxygen also. There was a factor of 1 plus that ratio missing. So that was a little mistake. And then the second one, somebody came and said, I said, for the mixture fraction, we're considering 2 streams. What if I have a burner like this, where you have a fuel stream, but the air is not, I mean, it's just there. So maybe the term stream is not so good. Maybe one can say we have 2 different reservoirs. One is a fuel reservoir, and the other one is air reservoir, and these start mixing. So I consider the air in the room here also a stream. So we had these relations here earlier. Why fuel unburned is the mass fraction of fuel in the fuel stream times mixture fraction, and a similar one here for oxygen. And what's interesting is that I can just draw these here as function of mixture fraction, and it gives me the solution. It gives me a solution as function of mixture fraction of the composition locally in this mixing environment. So if I just turn this on, now it's not burning, but locally I have a concentration of fuel and of air and so on. And if I would know the mixture fraction, I can tell exactly what the composition is. Okay, so that's what this tells us already. So in the unburnt, but now I would ignite it, and then we can also see what the composition is. So this is the stoichiometric mixture fraction. By the way, I didn't say anything about the values. So the typical values are for methane, the stoichiometric mixture fraction is 0.05, 0.055 actually. So very small, because the mixture fraction gives you mass ratio. And we said earlier, you always need a lot of oxygen, a lot of air, for a certain mass of fuel, which is why then the mass ratio or the mass fraction of fuel is very small, okay, for stoichiometric conditions. So for hydrogen, it's even much smaller. For a larger fuel, heptane, it's 0.062, which means for most hydrocarbons, it's something like 0.05, 0.06, okay? So it's usually a small value. It changes if you have exhaust gas recirculation, if you add some oxygen to the fuel stream and things like that. But for typical hydrocarbon air combustion, it's a small value. Now, if we can divide this up into 2 questions, one for mixture fraction smaller than stoichiometric, which means it's lean or fuel deficient, and larger than stoichiometric. If you first consider the lean case, then in the lean case, you have the definition of mixture fraction, but on the lean side, for fast chemistry, infinitely fast chemistry, the fuel is all consumed. Which means if we assume infinitely fast chemistry, then on the lean side, the fuel, when combustion takes place, the fuel is all gone, and there's oxygen is left over. So if in this relation here, I set YF equal to 0, I can solve this here or I can divide it actually here by the Z stoichiometric. You see then the denominator goes away, and then I can solve this for YO2, which is then here a function of 1 minus Z divided by Z stoichiometric. So this here again, so YO22, that's the mass fraction of oxygen in the oxidizer stream. For air, this would be 0.23. So these are known values. And so you see, I know the oxygen mass fraction as function of mixture fraction, okay? Now, I can do the same thing for the rich side. You know, it's the same thing. Now, oxygen, for infinitely fast chemistry, at complete conversion, oxygen is 0, and then I can solve this relation here for the fuel mass fraction. For the combustion products, CO2 and hydrogen, we use the fact that element mass fractions are conserved over combustion. So I can write the element mass fractions here for carbon, hydrogen, and oxygen as function here of the fuel, unburned fuel mass fraction and oxygen mass fraction. And I can also write these for the burnt case. So carbon only, and the unburned, carbon only comes from fuel, hydrogen only comes from fuel, oxygen only comes from the oxidizer. And then in the burnt case, carbon comes from the fuel and from CO2, hydrogen comes from fuel and from CO2, from H2O, and oxygen comes from oxygen, CO2, and H2O, okay? And now, before and after combustion, these element mass fractions must be the same because they're conserved over the combustion process. Elements are conserved. So this here is equal to this. And you see we had a relation for this already in terms of mixture fraction. We had a relation for this in terms of mixture fraction. So I can solve this now for CO2 burnt. Okay? That gives me the CO2 mass fraction. And that I can do this again for mixture fraction smaller than stoichiometric, larger than stoichiometric, and this is what I get. I can do the same thing also for hydrogen mass fraction, which gives me then the mass fraction here of water. Okay? So this, as I said, this you just use the relation. This ZH after combustion must be the same as before combustion. We plug in this thing here for the relation we had for this YF unburnt, for YF burnt, and then we can solve this for YH2O burnt. And we can do the same thing here for the oxygen after combustion also. So once we have done this, then we have here these relations, and I can plot these here again as function of mixture fraction. This is not here is not quantitative, but it is quantitative here. You have these stoichiometric values, which you can compute, and then this is what you get. So this means that now even if I turn on this flame, if I know the local value of mixture fraction, and I assume one-step global reaction or complete conversion of fuel and air to combustion products, then I know the mass fractions at every point, at every location in the flame. Okay, so that's called the Birke-Schumann solution. It gives you for one-step global chemistry, gives you the complete solution as function of mixture fraction, and it's just based on the coupling function basically. Really, it all comes from the coupling function, and it is this is a solution for infinitely fast irreversible chemistry. And you see here at stoichiometric conditions, so this here would be the oxidizer, this is the fuel, where here, for example, CO2 and H2O are 0. Then at stoichiometric conditions, CO2 has a maximum, water has a maximum, and fuel and air are completely gone. So the fuel goes like this, and then here it's 0. The oxygen goes like this, and here it's 0. And nitrogen is not shown here. It would just go from here 77% linearly all the way to 0. So what's interesting here also is two things, really, is that, well, we know the solution, but secondly, that these species here, they vary linearly with mixture fraction. That's also something that's very nice. Because, why is that? Because here, in this particular case, we'll see this later, that reaction rates are proportional to the curvature of these functions, okay? And you see the curvature here goes to infinity Well, we assumed infinitely fast chemistry, so the reaction rate is infinitely large, which is why for infinitely fast chemistry, reactions only happen in this sheet at, you know, zero volume, basically. Why? Because you need an oxygen and you need a fuel molecule. They come from different sides, and as soon as they see each other, they're being converted. So fuel and oxygen cannot coexist here. And the reaction zone is infinitely thin, which is why this is also called a flame sheet model, because the reaction zone is infinitely thin. That is not, of course, an assumption here that the chemistry is infinitely fast. But again, if you look at, take a cigarette lighter. Cigarette lighter is very similar here to my diffusion flame. And you will see that the reaction zone, which is the blue region here, it's very, very thin. It's a fraction of a millimeter. It's really thin. At high pressure, it gets even thinner, okay? So in a gas turbine, this thing is really super thin. And why? Because of this. Because the chemistry is not infinitely fast, but in typical application, the chemistry is relatively fast, okay? So that's flame sheet model. And here you see there's no curvature. It means there's no chemistry going on here or here. And the reason why what happens here is just transport. Why does this go to zero? Because here I consume it. So this diffusion, a diffusive flux of fuel from the fuel stream into the reaction zone. Okay, diffusive flux. And so this here is all diffusion. And because mixture fraction and species, they diffuse in basically the same way, they have a linear relationship. Okay? Yes?
Is this model also applicable for premixed flame?
No, because premixed flame would be only one point here. It would be, premixed flame is very different, right? No, this is not for premixed flames. This is only for diffusion flames. Okay, so in premixed flames, actually it's a funny thing. There is a thing that's called cold boundary difficulty. So in premixed flames, if I would assume infinitely fast chemistry, I have fuel and air. There's no unburnt anymore, okay? So you cannot make that assumption, really, for premixed flames. Even if you assume one-step global chemistry, it says fuel plus air, fuel plus oxygen goes to products, and it has a certain reaction rate, which is proportional to exponential minus E divided by RT. So it's never really zero. So if I think of a premixed flame and I go away from the premixed flame, the residence times get longer and longer for a premixed system. So at some point, it should react. So very often we try to use the simple picture of we have an infinitely large flame. I mean, the unburned goes this way to infinity, burnt goes that way to infinity, and in between we have a flame that burns, but there's no infinitely far away unburned stuff for one-step global chemistry, because it will always react at some point. That's called the cold boundary difficulty and analysis, but maybe that's just on the side. Yeah.
Assuming that reaction doesn't happen until the mixture fraction becomes stoichiometric?
Yeah, that's a good question now, and you can actually answer it yourself. The question is, are we assuming that there's no chemistry going on until we reach stoichiometric? And the answer is no, we're not assuming this. Why don't we need to make that assumption?
All the fuel is reacted by.
Because there's no oxygen here. Reactions cannot happen. There's no oxygen, okay? The fuel cannot penetrate on the oxidizer side because they can't coexist, okay? Because they would react instantaneously. And the oxygen cannot penetrate on the fuel side, again, for the same reason, okay? So we don't need to make that assumption because the only reactions can take place here are fuel plus oxygen goes to product, and where there is no oxygen here, there's no fuel here. They only meet right here, and which is why at this point, the concentration of both has to simultaneously go to zero, okay?
But if you would zoom in, you would have richer or linear combustion due to thermal heat
Say that again?
What I'm saying is, in a real case, you can.
In a real case, yeah. So in a real case, because chemistry, the chemical rates are finite, they're not infinitely fast, you have an overlap here of fuel and air. But that overlap is very small because chemistry usually is relatively fast. What happens if the chemistry becomes slow? That's interesting. We'll talk about this later. That's interesting because if you assume one-step global chemistry, then the oxygen doesn't change very much, and the fuel will penetrate into the lean region. If you look at experiments, that's not the case. Experiments will show you the fuel actually doesn't change very much, but the oxygen penetrates into the fuel. And that's what multi-step chemistry will also tell you. Okay? So that's one indication that one-step chemistry is just not right. Yeah, but so you have, we call this oxygen leakage into the fuel. Okay? Okay, so then this is the end of this lecture. We start a new lecture now. Which is on the thermodynamics. So here again, now we talk about thermodynamic quantities first. I'll try to do this fast. There are some important aspects of mixtures when we talk about thermodynamic quantities. Then we talk about first law of thermodynamics, which will essentially tell us what the flame temperature is. And then we talk about the second law of thermodynamics, which will tell us about the equilibrium, chemical equilibrium. So, first law of thermodynamics, of course, it tells us that energy is conserved. We write it typically in terms of a balance of energy. We have internal energy U, or this is a change of internal energy U. We have volume change work, which is PDV work. The work we call dW. And then we have heat transfer. The amount of heat we call Q, and a change of or heat transfer we call dQ. Here we use for the state variables, we use the total differential, the Roman D. For process variables like heat transfer, which is not a state variable, which is a quantity that describes the process, we use this delta here to just indicate this is not a total differential. And then we can write the first law of thermodynamics as du. The change of the energy in the system is equal to the heat transfer in or out of the system and the work. And here for simplicity, we use PDV work is the work we're considering here. Then we have defined enthalpy as U plus PV. For an ideal gas, PV is equal to RT divided by the molecular weight, and which means the enthalpy is U plus RT divided by M, which means really that because U is only a function of temperature for an ideal gas, it means also enthalpy is only a function of temperature. That's what we call a calorically ideal gas. Means it's only a function of temperature. Then we have an internal energy for each individual species and an enthalpy. And so this here is the specific internal energy, means energy per unit mass. That times the mass fraction, and the sum overall gives you the specific internal energy of the mixture, and also the internal energy, the enthalpy of the mixture, the specific enthalpy of the mixture. This here we just said already. This I mentioned already. Internal energy and enthalpy are only a function of temperature for a calorically ideal gas, and which means really, if we write the total differential, if we have, if we say H is a function of temperature and pressure. That's what we would usually say. Then we write the total differential dH is equal to dH dt at constant pressure plus dH dP at constant temperature. Sorry, dt dP. Now for this here is what we call dH dt at constant pressure. We call this what? Cp. Everyone knows this. Good. So for an ideal gas, this depends only on temperature. So this is 0. So dH is equal to Cp dt, which means I can integrate this. I can integrate this, and the integral of this is shown here. So H is equal to a reference value plus the integral from the reference temperature to the, or I would write it like this. So if I integrate this from a reference temperature, from a reference point, let's say, to a given point, given temperature, T reference on both sides, then I have H minus, or H of T minus H at the reference point, or H of T reference is equal to then this integral Cp dt from T reference to T, and this is what this says. Okay, so usually in thermodynamics we don't talk about multi-component systems. We don't care very much about this reference value. Here the reference value is important because it tells you the enthalpy, the chemically stored enthalpy in a molecule. So if you look at this relation, then it says that the enthalpy that is in a molecule, or if you look at let's say the enthalpy that's in a molecule is what's chemically stored in the molecule plus the thermal part. Okay, this is just the thermal part, which is the thermal energy that's stored somehow in the molecule. So the reference temperature here is usually this says it's usually it's arbitrary, of course. It's either 0 Kelvin or 298.15. But typically it's something like this. Typically it's something like close to ambient conditions. That's what it usually is. So this was specific enthalpy, means enthalpy per unit mass. I can do the same thing, enthalpy per unit per mole. Okay, and so that is nothing new. And then I have to evaluate these quantities, and they're typically tabulated. The enthalpies, reference enthalpies of chemical species, they're usually tabulated. The reference enthalpies, they need to be consistent somehow among the different species. And the way this is done is you choose a reference enthalpy for each element. You have to, the consistency comes by having them consistent among the different elements. So you have one reference enthalpy for hydrogen, one for oxygen, one for nitrogen, and one for carbon. And we typically use the hydrogen molecule, the oxygen molecule, nitrogen molecule, and solid carbon, because that's the state you have at ambient conditions. And the reference enthalpies of these are set to 0. Okay, so reference enthalpy of hydrogen is typically set to 0. So that means then the reference enthalpies of combustion products, they are typically negative because in the beginning I have some, hydrogen plus oxygen together, they have an enthalpy of 0 at ambient conditions here. They have a reference enthalpy which is 0, and if I burn them, they produce thermal energy, so their final enthalpy must be lower, which is why combustion products here typically have negative reference enthalpy. If I want to evaluate the enthalpies, the thermal part of the enthalpy or the total enthalpy including the reference part, then we do this here with these polynomials called, typically people refer to this as the NASA polynomials. So you have a polynomial for Cp, one for the enthalpy and one for the entropy. And you see already that these must be related to each other because dH dt is equal to Cp. So if you take this here and take the first derivative with respect to temperature, you basically get this. So you see that this here has one more coefficient. So typically here Cp, you have 5 coefficients, one extra coefficient for the enthalpy, and then one extra coefficient for the entropy. And then entropy, of course, depends not only on temperature, it depends on temperature and pressure, which is why there's also a pressure term that is added here for the entropy. Okay? So these coefficients, where do you get these from? You know, there are tables you can find in the internet. So if you look for or publications, but they're very easy to find for many species. Look at new fuels, for example. I mentioned earlier we do a lot of work on new biofuels where we don't have these values, then they need to be computed, or there is methods called group additivity theory that allows you to estimate these values, you know, from the fuel structure. So this is how these polynomials look like. Here is just these coefficients, and the coefficients, typically you have one set of coefficients for the range below 1000 Kelvin and one set above 1000 Kelvin. One needs to be careful. They are, so this here, for example, says this here goes from 1000 to 5000 Kelvin, which means if I ever want to use this above 5000 Kelvin, it gives me garbage. Okay, so even if you have numerical code that during, you know, the finding a convergent solution goes to temperatures above 5000 or outside of this range, maybe it's not 5000, maybe it's lower, then the values might be garbage because, you know, polynomials, if you leave the range for which they're fitted, they do crazy stuff. Same here for the lower temperature. If you go below 300 Kelvin, then also you can get crazy stuff. Anyways, this is how these look like, and that's how we determine these. So we take here Cp, H, and entropy. We take these as given because it's easy to compute these for the individual species if we know temperature, and for the entropy, temperature and pressure. Okay, so if you write the first law of thermodynamics here at constant pressure, then we have first law is du is dq plus dw. And the definition of H is u plus pv. Product rule will give me dH is du plus vdp plus pdv. And so this term here is 0 at constant pressure. So this is equal to du plus pdv. But du plus pdv, if this is pdv work, is equal to dq. So you see, at constant pressure, dH is equal to dq. dH, so delta H here for a reaction, I can write this as the sum of all the enthalpies of the individual species times their stoichiometric coefficient. And so if I execute a reaction, you know, I can measure the dq, and from that then I can determine here these so-called reaction enthalpies. So for example, I have a reaction here, CO plus 3H2 goes to methane plus H2O. Say I have a reaction like this. I execute this, I measure how much CO and hydrogen I used, and then I measure the Q. Q is equal to delta H, and the delta H is just the enthalpy of the products minus the enthalpy of the reactants. And so that if I measured this quantity, it would allow me to say something about the individual enthalpies here. Or vice versa. If I know these, then it allows me to say something about the change or the dQ, how much heat is released. We said earlier that we somehow need to have these reference enthalpies, and you can determine these in the same way. So for example, if I have a reaction here, solid carbon plus hydrogen gives me methane, then the change in enthalpy here is equal to the heat release, dQ, and that's equal to the enthalpy here of methane minus the enthalpy of solid carbon minus that of hydrogen. And you see, so these two are by definition are zero, which means if I execute this reaction and I measure the released heat, it allows me to determine the reference enthalpy of methane. Okay, and that is now basically the reaction enthalpy. That's the energy that's stored in methane relative to hydrogen and carbon, or vice versa. And I can do this, for all other species, C plus O2, give me CO2, and so on. So I can always, each species, I can always, put it together by the species which have a reaction enthalpy defined to be zero. Okay, so that allows me then to define the reference enthalpies of all possible species. So they can be tabulated, and so here these are the reference enthalpies at 298.15 for different species. Here you see, for example, hydrogen, nitrogen, oxygen molecule. They're all defined to be zero, as we said. And then relative to this, you see here H2O is negative, CO2 is negative, and so on. And so, for example, if you take, now you can compare these with each other. So, for example, you could look at this here, C2H4 is positive, C2H4 plus hydrogen. If you put these together, you might define a reaction that is C2H4 plus hydrogen gives C2H6, and you see that this now is negative. Okay, hydrogen was zero, so this just means that this here has a lot more energy stored in the bonds than this. Okay, so unsaturated species, they have they carry a lot of energy. And so on. So it's interesting to compare these values with each other. You see, for example, also, if I want to break up O2 to 2O, I have to add a lot of energy, okay? Or if I have the recombination of 2O, it comes with a strong heat release. For example, you see all these things here in this table here. It's almost trivial to see this, so it's interesting. So we define the reaction enthalpy. We define this as delta HM. This is the enthalpy that, or this is the difference of the chemically stored enthalpy during a reaction. So if delta HM is negative, it means the reaction is exothermic. If it's positive, it means it's endothermic. And so we can define the lower heating value, which is nothing else than the reaction enthalpy, or the chemical energy that is freed during the reaction, divided by the molecular weight. So this is per unit mass, rather than this here is per unit mole. Okay, so this is the lower heating value. We can also define the higher heating value. Why do we need the higher heating value? Because typically in combustion of hydrocarbons, you form water. And of course, it's different. The energy is different if the water is liquid or if it's in vapor form. So if I manage to condense the water to liquid form, then the heat release is larger, right? Because that gives me extra energy. And if it's in vapor phase, it's lower. That's why we call this the lower heating value is when the water is in vapor phase, higher heating value when the water is in the liquid phase. So they relate to each other by, here you see this is the lower heating, the high heating value is the lower heating value plus so this here is the heat of vaporization, times basically the mass of H2O that I can form from the given fuel. Okay. So typically, this year is about 2,000 joule per kilogram, and if you add up these numbers, then for typical hydrocarbon, the higher heating value is maybe 10% larger than the lower heating value. So it makes a difference. This leads to interesting aspects. You see here, this is a so-called condensing boiler. Condensing boiler. That's the new heating technology. This is a typical system that you have in your house that burns natural gas and provides heat for the house, let's say. And condensing boiler here from this company, Buderos. And look at what this says. The efficiency is up to 108%. Efficiencies usually are defined, I got this from the web, this is what you find online. So efficiencies usually are defined to be within 0 and 1. But this is larger than 1. Efficiency higher than 1. This contradicts the second law also, but also the first law of thermodynamics, you would say. But the way they define it is they say this is the energy we get compared to the lower heating value. Okay? So in the combustion process, you usually the combustion efficiency, how much of the chemical energy you can convert into thermal energy, that's typically close to 100%. And if I then take the water and condense it, I get 10% more. This is why they say. So they have a combustion efficiency of 98% plus about 10% because they compare it to the wrong value, really. So the way they do this is, I have a system like this at home. So you have the exhaust gas, goes through the exhaust pipe, to the roof. And it is in a plastic tube. And while it goes up, it cools down, so the water will condense, which leads to a heat release. And then the combustion air actually comes through a concentric tube, which is then heated up by whatever goes out. So that cools down the inner part. So when the combustion air comes in, it's preheated a little bit already due to this condensation energy. Okay. Anyways, from this then we can, these considerations, we can formulate the first law of thermodynamics and try to compute what's the temperature is after combustion. Because now we have with this reaction enthalpy, we have the amount of chemical energy that is freed. And that chemical energy that will then be converted to thermal energy, and so it allows us to compute the temperature. So again, we write the first law. We want to consider a system that's adiabatic and at constant pressure. And then we burn fuel-air mixture, and we try to see what's the temperature. And then from the first law, we get du is minus pdv. Again, dH is equal to du plus pdv plus vdp. And if we insert here du is minus pdv, you see these first two, they cancel each other. This last one is 0 because we consider a constant pressure, and it means that in a constant pressure adiabatic system, the enthalpy doesn't change, okay? The enthalpy is constant, so we can say in this system, we know then the enthalpy of the unburned is the same, or the enthalpy is the same before and after combustion, okay? So the enthalpy of the mixture is Y times Yi times Hi, and then the sum over all species before combustion, after combustion. And then we said the enthalpy actually has two parts. The first part is the reference enthalpy, and the second is the thermal enthalpy. And now we see what happens during combustion. I have some species that have a high reference enthalpy, meaning they have a lot of chemical energy in their bonds, stored in their bonds. These are then converted, so this would be the fuel and the oxygen, or the oxygen 0, but the fuel is high. And then these are converted to CO2 and H2O, and they are strongly negative. And so this means this energy that's stored in the bonds from fuel and oxygen to products, it will go down. So this reference part here, the chemical energy through the combustion process, this goes down. But because the enthalpy is conserved, or it's the same before and after combustion, it has to end up somewhere, and it will end up here. This is the thermal part, okay? So after combustion, the reference part, or the chemically stored part, is very low after combustion, but the thermal part is very high. So that's what this term says. So if we insert these here on both sides, then I get 4 terms. I get 2 terms before combustion, 2 after combustion. I group them, so I have the chemical energy here on the left-hand side and the thermal energy here on the right-hand side. Okay? And then you see this is the Cp of the mixture, you know, they come from the individual Cp's of the, so Cp itself is a function of temperature, and then I have the mass fractions. We computed the mass fractions in the last lecture. So this shows again the change in the chemical energy will show up as a thermal part. And then I can take this equation here and evaluate the two sides. Let's first look at the left-hand side. The left-hand side then, this here, I can determine from the coupling function again, okay? So this was the coupling function. I integrate this, I get this, okay? So you see we're getting close. This looks very similar to this. And then I multiply it with the reference enthalpies of the individual species. Then I have this. And then I just get the sum over all species. Then sum over all species. Then you see I have this term. And here on the right-hand side, this times the reference enthalpy, sum over all species gives me this. Okay? So that is so that now relates the, you know, all species here to the fuel, and the fuel after combustion, let's say for a lean mixture, the fuel after the combustion process is all consumed for a lean mixture. So this would be 0, and this is the initial fuel mass fraction I have. Okay, I know that. That's the one parameter I have to fix. Okay, so we can evaluate. So these are all known quantities then. Then the right-hand side, you see we have these integrals. For these, we assume, or maybe first about this right-hand side here. So we have this sum here. This sum here, we call this then the heat of combustion. This is the heat that's released during combustion. And this is a function of temperature also, but it turns out it doesn't depend very strongly on temperature. So very often we evaluate this just from the reference quantities. That's very good because the reference enthalpies I can just get from my table. So I can evaluate this here very, very easily. Then for the second integral here, these integrals. We just want to assume Cp is constant, and then we can just evaluate these. So we assume the unburned temperature here is the reference temperature. Or I define this as the reference temperature. I assume that Cp is approximately constant, and I assume Cp is equal to 1.4. And then you see this here is just Tb minus Tref minus Tref minus T. What is this? Tb minus Tref minus T unburned. I don't know what this. Oh, minus T unburned minus Tref. So this here actually, if I assume this is the same, this would be 0. And then I have just Tb minus Tref is the, or minus Tu is the right-hand side evaluated. And if I equate these, then you see I can compute Tb. So Cp to the other side, I get Tb minus Tu is this quantity here with this heat of reaction, which, as I said, can be easily determined. So this here actually, this you can look at. So we had earlier a coupling function among different species. You can look at this also as a coupling function between species and temperature. That's an important coupling function also that we often use. And basically what it tells you is the same thing. When I have a chemical reaction, I consume a certain amount of fuel. It means I consume a certain amount of air also. And it also means at the same time, each time I execute this reaction, that much energy is released, which means I get a temperature increase by that much. And so this also you can look at as just a coupling function, where here we just set here this Y fuel burned, we set this to 0. You can do the same. So this is for lean mixtures. For rich mixtures, you can do the same thing by using a coupling function here that's based on oxygen, but everything else is the same. And then you end up with something like this. Okay? So this tells us then we call this the adiabatic flame temperature, meaning the temperature for an adiabatic system with complete conversion from fuel to fuel and oxygen to CO2 and H2O. Okay, and this is an example now. So the nice thing about this is that, it's all, you don't need a computer to do this, a simple calculator or, just a pencil. With these tables, you can evaluate this. So for example, here methane plus O2 gives CO2 plus water. We can determine the Qref here is just these, based on these reference enthalpies, which we can get from this table I showed you earlier. So this is the Qref here for this. This is the amount of energy that's released. And then stoichiometric fuel-air mixture. Stoichiometric, this would be the fuel mass fraction. We assume Cp is 1.4, and this is a molecular weight. And then and then we can just plug this in, and it turns out here for 298 Kelvin unburned temperature, we get about 2,261. And the real value is more, if you do everything, as accurately as possible, you end up with something like 2,225 Kelvin. That's a good number to remember. Stoichiometric methane air combustion. At stoichiometric methane air combustion, adiabatic complete conversion gives you about 2,222 Kelvin. Okay, easy to remember. So, and you see that this simple way of doing this is actually quite accurate. Okay. Let's see. So now what we can do also, I have this relation between the temperature and the fuel mass fraction. and for lean mixtures, and temperature and oxygen mass fraction for rich mixtures. But earlier we had these relations here between fuel mass fraction, oxygen mass fraction, and mixer fraction. So I can plug these in here, and then I get a relation between the temperature and mixer fraction. Okay? So if I assume, if I don't assume fuel and oxidizer at the same temperature, one could be hot, the other one could be cold, then there's a linear relationship. The temperature has a linear relationship between the oxidizer and the fuel temperatures. And, you know, if I then just plug this in, then I get these relations here. TB is TU plus, you know, this here, function of mixer fraction, or for lean, for rich conditions, depends here on the oxygen concentration in the unburned mixture. Okay, and this gives me also the maximum temperature. If I insert here Z stoichiometric, gives you the maximum temperature, and here for both have to be the same, of course. And then I can plot this also as function of temperature. And you see, as function of mixer fraction, you see temperature as function of mixer fraction is very similar to CO2 as function of mixer fraction. And you know, this maximum value here, that would be the 2,222 we just had. If the unburned temperatures here are equal to 298 Kelvin. You see here, this is the unburned temperature, which assumes here, in this particular case, that the oxygen mass fraction, oxygen temperature is a little higher than the air temperature. This is what you would have in a diesel engine, where you compress the air is hot, and then you inject cold fuel into this. So that would maybe look a little bit like this. Okay? So that is then the Burke-Schumann solution for the temperature, again, for an irreversibly infinitely fast reaction. So that, again, is interesting because now, if we locally know the mixer fraction in a diffusion flame, then using this flame sheet model, we can determine temperature and all mass fractions that appear in this one-step global reaction. We can determine these quantitatively. Okay? So that's, you could think of this as the simplest combustion model, where you solve an equation for mixer fraction, and then you know, locally you evaluate temperature and mass fractions from this model. Okay. Okay, so this gives you a few examples here for what that maximum temperature, adiabatic flame temperature is. Methane, we just said here, you know, from this formula, 2,260. Ethane, about the same. Now, unsaturated species, we said earlier, you see already in the enthalpies, in the reference enthalpies, that they have carry more energy. So you see this will be 2,400. Acetylene here, 2,600. And this here is a saturated species, propane. Again, that's very similar to methane and ethane. Okay? This is why, we'll see this later, when we talk about flames, we will see that the burning velocity of a fuel depends very, very strongly on the adiabatic flame temperature. We'll see this later. And here you see these unsaturated species, they have very high adiabatic flame temperatures, which is why they burn so fast. Acetylene burns very fast. And ethylene also burns relatively fast. Okay? Hydrogen also has a high adiabatic temperature, which is another reason hydrogen burns so fast. Okay? Any questions about this? Okay, so then we will probably not finish this, but we have about 5 more minutes, so maybe we can start talking about chemical equilibrium. I said we use the first law of thermodynamics to determine the flame temperature, second to determine equilibrium conditions. For now, we said the temperature you get at the end, it is the temperature you would get if you take all the fuel and air at stoichiometric conditions and completely convert it into CO2 and water. But in reality, this would never happen. You always have reactions going both ways. And they go forward and reverse, and you will never convert all fuel to an oxidizer to products. You end up somewhere in between. Where you end up, that depends. So after infinitely long time, you reach chemical equilibrium, and that is somewhere in between. And where that is, that depends on the local conditions. And how that depends on the local conditions, that equilibrium composition, that we can see from the second law of thermodynamics. So, so for now, we assume complete conversion. Chemical equilibrium is a more general formulation. It also assumes, by the way, chemical equilibrium, it assumes infinitely fast chemistry, but not complete conversion. Infinitely fast chemistry in the sense that in order to reach equilibrium, you need to wait for an infinitely long time, okay? Or you make the chemistry infinitely fast, okay? That's the same thing. Okay, so infinitely fast reaction is what we call then chemical equilibrium, and in reality, of course, reactions are not infinitely fast, and then kinetics comes in. As you know, everything goes towards equilibrium. We always move towards equilibrium. At some point, we'll all be, you and I, we'll all be a big homogeneous soup flying through space, okay? And the reason why we are not a homogeneous soup already is because chemistry is finite, a finite rate. Things don't happen infinitely fast. This thing here is made of wood, okay? It's carbon. We have air. Actually, this wants to burn. This will ultimately, this wood and this air will make together CO2 and hydrogen, and H2O, mostly, okay? And the reason why it doesn't happen is kinetics. If I make kinetics fast a little bit, yeah, I can demonstrate, maybe. Then it does that, okay? And maybe you see here a black mark from last time I taught this course. I got into trouble, so which is why I don't do this anymore. So maybe we'll do this next time. One thing I want to tell you is 4 years ago I taught this course, and 4 years ago I taught this course, and during my lecture, so the World Championship was going on 4 years ago. Okay, soccer. Who is into soccer here? Okay, so you know a lot of people are into soccer. So during my lecture was the Germany-US game. This time, unfortunately, it's not going to happen because the US didn't qualify. But 4 years ago, it was during my lecture, and on the first day, we made a deal in the class that we skipped some breaks or whatever. I can't remember what exactly we did, but we managed to go. So we all together went to a local sports bar here, or bar, this little brewery, and we had beer and watched the game. And the game ended 2-0 for Germany, which was good. We were the first in the group, which we wanted, and the US advanced also. Everyone was happy. We had beer and everything was good. In the afternoon, maybe it was not so good for the students, but it was great. This year, and so if you want to see the deal, so the lectures are on YouTube, and if you watch the first lecture, the first day, we missed to cut this out of the video, but it's all in the video. And I tell the students, don't tell Professor Law. Don't tell Professor Law. And then later on, it's online, so maybe he figured it out finally. So on Wednesday, again, is the German game. But I think it starts at 10 o'clock in the morning. And I couldn't figure out a good way to move things around, skip breaks or whatever, so that we can all go and watch this game. If anyone has a good idea, let me know. Maybe we can still figure something out. Okay, good. So I'll let you go. Enjoy lunch, and see you tomorrow.